The universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hey, welcome everybody, and welcome to you too, Tara. How are you over there?
Hello, Mark. Hello, everyone. I'm doing great, thanks. Glad to be here.
Oh, great. Yeah, tonight we're gonna have a lot of fun. This is like 2 weeks in a row we're doing a live show. I mean, sometimes things come up and you just can't do it, right?
Mm-hmm.
Well, we're gonna try and continue the trend if we can.
Okay.
We're
so trendy, Mark.
I know we are just trendy.
Yes, we are.
So at my end here in Connecticut, across the country from you, we've got flood warnings. People's cars are actually filled with water. They're up to the windows and filling in the car with water in some places. So there's actually a ton of water coming from the sky, and the worst might be over. But I took a drive out earlier, and probably not the best idea because some of the roads were washed out, and I was still driving on like this, like oh, look at that!
Are you driving through the washes and stuff?
Yeah, I've done that before too out there. Okay,
don't do that.
Yeah, I did. I drove through a washout there. Okay, there's Bill. What's happening,
Hey, Bill?
Bill, this guy,
Mark.
This guy is our amazing producer, by the way. Let's show him some love.
Mark is my neighbor that way and a little bit to the north.
Yeah.
Mark, if you see me disappear, we have severe storms about to hit us in the next
week.
Well, if we go away, then people will understand that it's not your fault, that it's the weather's fault.
It's getting dark now, but just so you know, you hear it?
I don't hear it, but no.
I think I did. A rumble?
Yes. So you know it's moving your way after. It's coming your way. So all that flooding and yes, I just have fun.
My driveway's gone. Okay. It was scoured out to a foot deep for 150 feet of my driveway.
Wow.
So it's now a ravine, and you gotta you go in, you gotta go. It's like this. It's like you go down my driveway. Boom, 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 boom. It's like, okay, all right, hold on. We're almost to the bottom of the driveway. Then you get to the bottom of the driveway, and then poof, one last little bump you got to go through.
Tara, I know that driveway well because I ran down it.
Oh my gosh.
Well, that's because I was chasing you, so it's not fair. You didn't really see too much of the driveway. You were running for your life.
Get out of this house.
The road when I left us. Beep beep. I was gone.
Meep meep.
Anyway, have a great show and love you both. And
thanks, man.
Love you, Bill.
Yeah,
Bye.
if something happens to our stream, it's okay. I got a whole show. We'll pick up where we left off next week.
Have fun. See you guys later.
Thanks, Bill, our esteemed producer.
Yes.
Actually, I think he's pretty steamed right now because he
might very humid.
He might lose the show. It's like being in a steam box too. That's right.
Oh yes.
Yeah.
Tell you, here in Phoenix today. It rained, for hours up early morning up till 7 or 8 this morning, and it was just been beautiful.
Well, you're in North Phoenix, so is it raining up there and not raining in like Mesa?
It's not raining now. It was raining this morning. So normally we get skipped. We're at the base of a mountain here, and the clouds go right around us, and so everybody else gets beautiful rains and monsoons, and we stay dry. But we got some rain last night. So.
Yeah,
but it's not flooding like you have. So
yeah, no. But see my experience with Phoenix from years ago was that, like in the early morning and at dusk, it might rain but then the water has no place to really go because there's a lot of areas that are on thicker clay-like soils out there. But
Mhm.
I don't know how that is these days. I mean, there could be a lot of differences.
Yeah.
know.
Well, up north, there's deserts everywhere. And so the sun has baked a lot of that. And if it's really baked ground, it is kind of like clay. It makes like little sandstone, right? But the water, you'll get flash floods in
Yeah.
just a small amount of rain. An inch of rain, I think, can make like 3 or 4 feet of water down the way. I mean, quickly, very quickly. So,
Yeah.
pretty
So
scary. So don't drive through ravines. So,
yeah. And what Tara was talking about before is kind of interesting. And there, you've heard them called arroyos. You've heard them called washes. You've heard them called "get the hell out of theirs." Okay. These are areas where water flows when it flows. And if you're in the
naturally.
middle of the desert, it could be blue sky all around. And all of a sudden
Mhm.
you hear water. And you look in one direction, all of a
You hear a
sudden
train.
it's like a train, and it's
Mhm.
actually a water wall coming towards you from
Yeah.
40 miles away,
Mhm.
traveling through this wash, which is this cut in the ground that the water travels in. And there's a lot of people that get in trouble with washes. Their cars get taken. Some lose their lives. Actually,
Mhm.
it's not that common. It's only common for people like me that don't live there. Because I actually got mixed up on the road out to the observatory, a Sky Tour live stream, and
Easy to do.
I started driving through a wash. Now I'm thinking, this is not the road. This is a wash. So looking at my GPS and my photographic map, I could see that the wash reconnects with the road farther down. So rather than back out,
Mhm.
thing to do,
Mhm.
continue going,
Ah. There's
and cactus went
oh.
on the windows, and I got what they call Arizona pinstriping on the car. And then I pulled out, got to a road, turned left instead of right, like I should have, and I got back to the main road and was able to come in from the other side to the property I was
Mhm.
trying to get to for the observatory. So, yeah.
You can get lost out there, and then you're in that middle of that arroyo or that wash, Mark driving, and here comes this wall of water, and you're
You
stuck.
got to abandon the
You,
car.
if you can, otherwise you got to wait for someone to come get you,
Yeah.
and then retrieve your ticket for driving in that.
Yeah.
So,
I don't want to be admitting it.
yeah.
But yeah, I mean, look, it's okay. It out there in the desert, there's no paved roads. Everything's a dirt road. And sometimes
If you're lucky.
these washes, or these arroyos, as people call them, will look just like a road. And you might see a fork. One fork looks identical to the other fork, but the right-hand fork is a wash. And it's going to end up going all these circuitous paths. And you see trees and cactuses overhanging. It's like, this can't be right.
Mhm. There's your clue.
I don't remember this, and you can't turn around. Because once you start moving, you don't want to stop because the sand is pretty dense or pretty loose underneath those tires, and you could end up stuck.
Yeah.
Even with a 4-wheel drive. So I just kept rolling, not wanting to stop. Okay, and I reconnected, but that was lucky. So anyway, that's my
Well,
stupid move of the
well, it's
trip
not your
that time.
vehicle, so it doesn't matter.
That is correct. That's right. That's right. No,
Not.
I treat other people's vehicles better than my own. Which
I
is
believe
I
that.
think I think that's the right thing to do, right?
Mhm.
So,
It is.
and what was I doing? I was going out to do some maintenance on the observatory. What observatory? I'm glad you asked. It's the Sky Tour Livestream Observatory. We are an
Oh.
established 501c3. Okay, she knows well. She's part of the organization along with
Mhm.
Marianne Robb. Okay, and together we've built a system that allows remote access, so we can access it. I can access it from here in
Yay.
Connecticut, out there where she is in I was going to say California, out in Arizona. And we run it from here, so we can run it from anywhere we can get a computer. And so the Sky Tour live stream is this clear night foray through the night sky, take you to the deep sky, and we see remnants of dead stars, dying stars, glittering jewel boxes that are clusters, rich clusters, wondrous phenomena in the universe like stellar nurseries, clouds of hydrogen gas that are ionized and look pink and red, and it's just stunning. The color in the universe is amazing. There's so much of it. Yeah. And those are places where life may eventually arise, because we started in a stellar nursery as the sun and other siblings, solar siblings, of which we've identified only one so far. Okay, we found an exact duplicate of the sun. We can't look at it in SkyTour Livestream because it's in the southern hemisphere.
Oh, darn it. When are we going to get a telescope there?
I'm working on it.
Okay, come on. Come
I
on.
know, I'm working on it. And this is also a stream where anyone who comes in can be in charge if they want to be, meaning, I'm always there. I'm an astronomer. That's what I got my degree in. Okay. So I will steer the telescope to wherever you say you'd like to look. And many times we get lots of requests in a night. And the only time that's hard to do is when we have a lot of people watching at the same time and their requests come in fast and furious.
Right.
So that's a problem. And we've had up to 5,000 people watching concurrently from around the world.
Incredible.
It's okay. Look, I'm just getting you can't hear it, but there's a buzzing. I'm getting another flood warning alert for my area. If you see water come through my
portholes.
There's my portholes up there.
Oh gosh.
Yeah. Or if you feel the ship starting to rock, then you know we're in trouble.
Isn't the ship supposed to rise with the water instead of come through?
Yes, but if it gets mobile, then we're going in trouble because I'm going to be like, hey, look out! I'll be right back. Yeah.
Well, let's hope that doesn't happen.
Agreed. So, what we do is we do our live streams. We show people these beautiful images, and for people that want to subscribe to our Patreon for a monthly fee, and for as little as $3 a month, we provide a monthly fee, and you get shout outs all the way up to personal guided tours of your own. And we've done at least one of those personal guided tours so far. And you have one too, because you're one of the principals in SkyTour, and so does Marianne. And that's available to you as well.
Yay, okay.
And so and then you'll find that we have an active chat. We have a good fair amount, actually, of moderators who are wonderful people, and they stop all the crap from coming through that might come through.
Thank you.
Yes, thank you for our mods. They're wonderful.
Thank you. Awesome mods.
Our KGRA audience is the best audience on planet Earth. There's no doubt about it. I will never argue with that. We've got good people out there, and we have wonderful people that have just joined. And for the people that just joined, I say welcome. Hi. So I think it's cool that you guys have joined. And don't forget to subscribe. This is our radio show on astronomy. That's a telescope right there. That's our East Coast telescope. Yes, that was in an observatory dome in my front yard. That was a real trick because the town was like, what's that big dome thing in the front yard? Is that a missile silo? And I would just look up and say, yes. They're like, what?
Because they're legal to have on the front of your house in Connecticut, right?
They are. They are.
Good. All right.
I'm not in the middle of a big town. I'm actually in a rural area. So you're driving along, and from a distance, it might look like the top of a grain silo or something. But then you get closer and you see it's only 5 feet tall to the dome, which goes up another 5 feet or so. And the whole building's about 8 feet in diameter. That's how it was. Well, anyway, the telescope is there because I sold a dome. I outgrew it. That equipment didn't fit nicely in that small dome. So I'm changing the approach. In the West, we have SkyTour Livestream, our West Coast Observatory. Yeah. We have beautiful images that we've captured there. A lot of people have seen some of the stuff we've captured. This is an example. This is called the Jellyfish Nebula. It's an old supernova remnant. Okay, here is another supernova remnant. It's a central part of something called the Veil, and the eastern part of that looks like this. I'm sorry, that's an eastern part. Yeah, I don't have the western part up right now. Actually, I think I do. Yeah, there's the western part.
Wow, pretty.
So
that's a long veil.
That is a long bridal veil. Yes.
Oh, it's gorgeous.
So that's the east side. There's the central part of it. And there's the west side of it.
Wow.
So we have the entire thing, and what we've done is mosaic it together so you can see the whole thing at once. And it's literally gigantic. It's massive. It's the size of several full moons across, which is amazing.
Wow.
So anyway, so we do stuff like that. We show crazy things like that. We just love it. But you see it happen live right in front of you.
Mm-hmm.
You know, that image, all those images you saw were 20 seconds long. 20
That's
seconds.
amazing.
Oh, thank you, Bill. And so with 20 seconds of exposure, we can actually capture a ton of things. And the way we do it, thank you, Bill. That's SkyTour Live. Yeah, SkyTourLive.com, SkyTourLive.org.
Mm-hmm.
Brings you to the same place. It's our portal. And what we do is we take a first shot, okay, and then we take a second shot of the same thing to another 20-second shot, align it with the first and stack it so that the stars align with each other, the nebulae align with each other, and then we build an image sandwich like this, doing stacking. And that stack does several things. Number one, it reduces the digital noise that is inherent with any camera system these days. And it also allows faint detail to be seen once that noise is eliminated. And the longer you stack, the more images you stack, you can get absolutely stunning images. And we have acquired some very stunning professional observatory quality images by doing this method. And the nice thing is, from SkyTourLive.org, you can actually go download them for free. And they're the raw images that we show you, the raw, semi-processed ones. If you want the finished processed ones, which are literally 500% better than these that you see, and you wouldn't know it until you saw them, then you can
They're all pretty.
Yes, you can be a member of our Patreon. Yeah, and get like $4 a month if you're at the lower tiers, and above that, you get access to the entire repository of our highly processed photos. And I know people that are like, "Whoa!" And then if you're really interested, you could go to our Etsy store, SkyTour Shop on Etsy, SkyTour Shop, all one word, and you can find these things emblazoned on water bottles, mouse pads, sneakers, blankets, lamps.
Everything you need to survive on a daily basis.
Right. If you want to survive the apocalypse, you got to do it with a SkyTour pair of sneakers.
That's right.
It'll allow you to trudge through the ashes of the old city.
I think that's a great idea.
Yeah,
Beautiful images. Well, and if you have access to the images, you can do whatever you want with them. So
that is correct.
So
we provide the raw images too. And you know what? We also have an app called the SkyTour Skygazer's Companion. And the app is coming out. It's not out yet. It was made by Isabella, one of our Bulgarian, hyperstar, I should say, members and participants in SkyTour Livestream. She is incredible, and she's also an artist. And she created this app and took several years of data going all the way back to early 2021, all the way to the present day, and put it in an app. So you can actually search on every time we looked for any of these objects I just showed you. Okay. And from that point, you can download them all, and then you can compare how they look and compare them with the oldest ones. And guess what? There are differences. She found stars that have vanished. How about that?
It's amazing.
Okay. And she found asteroids in our old imagery. Okay. So she's done some real science using our data, and we've got years of it out there. So it's pretty cool. Pretty cool to see. SkyTour Livestream was also named in an award by Las Cumbres Observatories, which is a network of observatories around the world, professional observatories, big observatories. And we have been awarded ours to use on a big telescope, so we can do some of our other research we'd like to do, which is really cool. And we're going to in fact, one of the guys on it just said to me today, I think it was today, that he wants to use some of our ideas to try and get some data. And one of the things I'd like to do is revisit some of these sites where we have seen stars that are missing.
Oh, cool.
And see what's there and compare it to our older shots we have and see if something else is different in there. Who knows? Maybe there is a very fast-moving dust cloud. Now, they're going to be light years away, potentially. But if there's one
Okay.
if there's one that's fairly close to our solar system, it's conceivable that over some months you might see a distant star, which is way farther away, changed by a passing cloud that may be passing between us and that star. But it would take a long time to see that, you know. But you never know.
Could be your lucky day, you know.
Yes, that's right. Like it was when we did the lunar eclipse. Remember
That's
that?
right. That's right.
Yeah.
It struck the
Remember?
moon.
That's right. We saw a meteor hitting the moon at the height of a lunar
Amazing.
eclipse. We caught that. And there was only 5 other people on the planet that actually caught it that
Wow.
night. I say people, groups. There's a lunar watch facility in Madrid, which actually caught it as well, because they were looking specifically for any potential lunar hits or
Oh,
meteors.
fun.
Yeah, and they caught them, you know. And had we been able to image in the infrared, we might have been able to acquire a little more information. But we're on record, though, as seeing it, and we can gauge the amount of light that we saw with our particular 10-inch telescope. And actually,
Cool.
that was this telescope right here that actually
Yep,
saw it.
that's right.
That one.
Cool.
It wasn't the Arizona telescope at that point.
What a good telescope.
I know.
Uh-huh.
Yeah,
Mhm.
this telescope, though, I think we're probably gonna sell, because we're gonna be replacing the East Coast with. We're not gonna put another big telescope like this here. We're gonna actually replace it with a smaller system. Actually, something more along the lines of what you see on top of it. That's a small 5-inch refractor. This is a Schmidt-Cassegrain. It's a mirroscope. The light comes in at the end here, goes down to the end, hits a mirror, comes up, hits a secondary mirror, and then goes down through a hole in the back where it comes out to an eyepiece or camera out here. A little different from how we're operating the one in the desert. You know.
Cool. That's interesting. Very cool.
Yeah. So the bottom line is that we have a lot of things we're doing, and I just talked to a guy named Tom Field earlier, and Tom Field is the creator of a spectroscopic analysis program called RSpec. Okay, and he sent me my new license key for RSpec, because we're going to start taking spectra with this new telescope. And
Cool.
so I have a filter wheel, and we're going to be rotating different filters through to do different types of imaging. Among those, we're going to be doing, filtered images like we have been of nebulae and showing you nebulae. And then we're going to have 3 other filters, which are going to be called narrowband filters. And they're going to be tiny slices, but they look at very, very important wavelengths. And together, when you put those images together at the end, you build a far more detailed image of a nebula than you might get with just a one-shot color camera.
Cool.
Really cool. It's narrowband imaging, and you can find things that are hidden within a nebula this way. So we're doing the shotgun now, Tara, but we're going to change that.
This all sounds so cool. It's so interesting. And I remember when that old telescope was up that you were using some of those filters.
That's correct.
And it really kind of just enhanced the experience in watching. It was just stuff you don't get to see every day. Very cool.
Yeah, I think people remember the first time I saw this. This is called the Eastern Veil. I had never seen this before, and when I actually looked at it for the first time with the telescope, all right, I was beside myself. I had never seen this before, and I was blown away by it. And I think people on the stream were probably a little surprised to hear my reaction. It was like, "Oh my God, I've never seen this." And here, I don't have the darkest skies. However, I do have that telescope fitted with a filter that allows you to cut through that sky haze and the light pollution.
Nice.
And you see what's hidden above,
The brown cloud, you mean?
Yeah, the stupid, the light pollutions in the sky from sodium vapor lamps and the new LED lamps.
Oh, yep.
Yeah.
The little
LED
bright
lamps,
ones. Oh.
Yeah. And when you have white light, many people know it breaks up into a spectrum of colors. And that spectrum of colors is something we're actually going to talk about tonight, actually.
Cool.
But before we do that, let me just say one more time that if you guys want to subscribe to us, join us on our Patreon at SkyTourLive SkyTourLive.org or SkyTourLive.com. We'd be happy to have you come on board. All right, that's the portal. All right. And if you want to email us, well, that's our email. Contact SkyTour@gmail.com.
Awesome.
You know.
And don't forget the giveaways, Mark. Did you
Oh,
mention
I'm
that?
there. I'm just about, yeah, you're right. That's a very good point.
Yeah.
Yeah, thank you for reminding me too. You can also join our Patreon. Go to SkyTourLive.com as well and join our Patreon. And if you wish to donate to our 501c3, there's a button right there, donate, and you can donate.
Thank you.
Now, one of the things we're also doing, and you'll see it when you go to SkyTourLive.com, as Tara just mentioned, is you'll notice that we give away equipment. We do. And because we have power, we have some really powerful people in our chat group, and people that are, we have people that work at SpaceX, and it's just incredible. And they provide us with equipment exclusively to give away. We've given away telescopes, binoculars, and we're going to be giving away night vision systems as well. That's down the line.
Oh, cool.
Yep. Full color night vision systems, by the way.
Great.
I have one here that I bought, and we're going to be able to do that as well for people. It's very important to get people out there looking up. And, a telescope is great, but sometimes they're daunting. And if all you want to do is go on a trip to Maine with your family, or a trip to, Utah, to Moab, okay, and you want to look at the night sky, sometimes a telescope is not the best choice. Just looking with binoculars, you'll just probably be pinned to the ground looking up, going, wow, and just move around and see all these amazing sights. You'll see nebulae, you'll see galaxies, because your two eyes with the same size lens in the end are going to bring in a lot more light than just one lens, looking through an eyepiece. Okay, one lens of the same size, you only see basically half the picture, right? You get the same amount of light, but only for one eye. The other eye's going, me too. Binoculars give you that dual look, and sometimes the universe looks 3D. Gotta say, yeah, really.
Versus the flatness. It would be neat to really see those dark dust clouds in real time, because they're closer than they appear to be to me.
And Tara's right there. They're actually closer to us than the bright things that silhouette them behind them, and the bright things behind them are nebulae and so forth. It's really cool, and so our West Coast site consists of the Sonoran Desert Scope right now, and we broke ground on Benson, Arizona site, which you guys know about. And I know it sounds like we're not making any progress, but we have been. Okay, we've been getting equipment and so forth, and we're going to be doing the install. Hopefully by September or October, I want to have Benson up and running. And I'm working with people here to make my housing that I want. And we're going to ship it out there like a little kit that we can assemble on site. So it's going to be kind of cool to see that happen.
Very cool.
Yeah.
It's amazing what can be done nowadays.
I know. I agree. And how quick it can happen too.
Right.
Yeah. So the observatory out there that we're making, right, the current one, we have a big slide off roof. It comes off the whole building, and telescope looks up and sees. But this new one is actually going to be one where it's literally 5 feet by 5 feet in size, and about just under 5 feet tall. So, well, what can you put in there? Well, we can pack a telescope in there, and the entire top of the building is going to come off like the top of a box and open up the whole thing to the night sky.
Cool.
That's going to allow us to see down to the horizon in all directions. Now, not that we want to, because in astronomy, we never look more, below 25 degrees or more.
Never?
Not usually, because you're looking through more air. Because the flat earthers don't want you to know that as you look toward the horizon, you're looking over the curve of the earth, and you're seeing through more air. So the stuff in the distance is fuzzier and more difficult to see, because you're seeing it across the curve and through a curved atmosphere. So you're seeing,
Makes
as you look
sense.
across toward the horizon, you're seeing higher and higher in the distant atmosphere until finally you're out of the atmosphere. But it's a lot more atmosphere than looking straight up. Looking straight up, you're seeing through about 90 miles of atmosphere, maybe 100. Okay. But looking along this way, you're looking at hundreds of miles of atmosphere. And that degrades your images. So we don't tend to look toward the horizon.
Yeah.
And when I was getting my degree, I never looked below 40 degrees. So I mean, I was literally constrained to an area like this in the sky. Oh, I liked looking at other things, but you couldn't get any good data, because you had all kinds of other factors creeping in, turbulence.
Yeah. So you're limited at what you can see, though. Is that why you have to work with other observatories around the world to see everything? I mean, how do we see everything that's out there?
I know. To see everything that's out there, we need observatories down in the southern hemisphere, don't we? Right?
And maybe one in Benson, perhaps. Yeah.
What's that?
Well, Benson is southern, but not hemisphere.
It's about 200 miles to the southeast of our current one.
Yeah.
And as a 200-mile distance, we are going to get a slight elevation in objects, but it's not that different. The same settings would work, but not well. So that's how it works. But it's so cool. And, building a building like this and putting it together, and if it wasn't for that person right there, this wouldn't have happened. And she's very, very like, oh, it was nothing. It was something. Fun. Yeah, don't let her tell you it was nothing. It was something. She was effectively the foreman out there, because she took charge and she made sure that everything was done on time, the right way.
Yep.
Okay. Marianne was right there by her side, working with her to make sure this was done. And I have nothing but praise. And I gotta say, when I first started doing this on my front lawn, SkyTour Livestream was me with a couple of people coming on to help me out. Okay. Well, the me disappeared very quickly as soon as she and Marianne got involved, because as soon as that happened, it became we and us. And now we consider everything. And if I want to get something, I consider what they think about it. And I let them make a determination with me, except for today when I spent $26. I put that in I did note, I said I forgot to mention it to you, and I'm sorry.
Yeah, I saw that. Just make sure it's on the expense report, Mark.
I know, I'm sorry. That's my fault. And I did it. And anyway.
We're kidding.
I'll pay for this later. Okay. No. So tonight, I know that we're spending a lot of time on this, but then again, it is important to understand. Now, in our observatories, okay, the thing that we look at generally are stars and nebulae and things, and that's the ones that the West Coast observatories will look at, because the sky is so dark out there. Out here, the sky is not as dark, so we're not going to get the same benefit with Deep Sky Observatory. Tempting as it is to put that telescope back in a building out front here, it doesn't give the same return, and people want to see more, and I'm okay with that.
Yeah, you spoiled us for sure.
I did. So what I'm going to do now is out front here, we're going to put a solar observatory. So we'll observe the stars at night in Arizona, and we'll observe the sun during the day in Connecticut.
Oh, fun.
Because solar images won't degrade, and they are very, very stark details that we can see. So I've got the solar telescope. I've actually had it for a long time, and I'm going to put a mount out here, and we're going to put an automated cover so that if I'm in Arizona at the time, I can actually run it here. Okay. And then
very cool.
I know, right? And then we're going to study the surface details on the sun, those prominences that leap off the sun. If we hear about a solar flare, we'll go observe it in real time, and you'll see the bright area on the sun that's currently exploding this flare. And when they explode, see, a solar flare is this amazing ejection of material from the surface of the 10,000 degree surface of the sun. Now it's many millions of degrees in the core, but the outer envelope of the star is just along for the ride, as we'll talk about in a little while. And so at that surface interface, sometimes magnetic field lines, because the star has a very powerful magnetic field. Okay. Sometimes those magnetic field lines get all twisted up. And when they break, they might break outward and spew material with them. because the material follows those magnetic field lines. So you have this normal sun, it's doing this boiling and stuff, and all of a sudden,
boiling.
boom, stuff comes right at you. And if we get one of these, it's called a coronal mass ejection, okay, a CME. That's high energy protons and electrons heading straight for us. And when it does that, what you see on the sun is a visible flare. And the flare is so bright sometimes that it overexposes the sensors on a camera that's trained to look at the bright sun. And it gets even so bright even that it overexposes those. And you'll see a bright spot, and then it expands and gets bigger. And the flare event happens over a short period of time. It doesn't happen in like 10 seconds or 5 minutes. It happens over the course of like a half hour, an hour, hour and a half. So when you hear there's a flare in the sun, you can say, okay, I'll go turn on the telescope. And by the time you get to it, it's still happening.
Oh, cool.
Okay? Yeah, the sun is big. It's over almost 1 million miles, 864,000 miles across. So these flares are like several times the size of the Earth. And when you see them from this distance, okay, it can be 10 times the size of the Earth. You actually watch them. You can see over a period of minutes, you can see them moving. But they look like they're not moving every time you look at them. And then if you come back 5 minutes later, you might see that. You might see that 5 minutes after that. It takes a long time. So it's pretty cool. Yeah.
Hey, thanks, Kathy.
Oh, what did Kathy say?
Kathy
said, oh, wow, Kathy. Well, thank you so much.
Yeah.
And rest in peace, James Lepresto, astronomy professor of Kathy. Wow, Kathy, thank you so much. That's sweet.
Yeah.
Yeah, this is the quality of the people we have here. They didn't have to do that, but they do. Yeah, and it's too bad that we lose good people. We lost Carl Sagan, my favorite astronomer, right? But he lives on because we make fun of him. Sometimes we'll say, we have billions and billions of stars in our universe.
If I close my eyes, it really is him.
Yeah, it really is not. So that's funny. So
that's great.
Yeah. So when we look at the stars, right? One of the things we might observe is that, and this is something that comes up often, that people ask me as an astronomer, and they say, how come we don't have any green stars? Did you ever notice that? We have blue stars.
Greens, who wants the green star? Well, there's some green. I mean, there was green in the veil, so there's green in the nebulas, but not in the stars. Okay,
that's right.
Okay.
We're going to talk all about that too.
Never thought about it, actually.
Yeah, and we see green and blue in nebulae, and we see red in nebulae. The colors of the universe are red, blue, and green primarily. Okay?
Kind of primary colors, sort of.
Well, they sort of actually are.
Sort of, not really, but
yeah. Well, if you think about it, RGB, red, green, and blue, is kind of what the colors of the universe are, just like you said. So there's got to be a reason for that, right?
Right.
Yeah. But the thing is, why don't we see green stars? This is interesting. Now, stars emit a full spectrum of light. And what's the full spectrum? Well, the full spectrum looks like this. Okay.
Ooh, pretty.
Yeah, that's red, orange, yellow, green, blue, indigo, and violet.
It's a rainbow.
Yeah, it is. That's right. Indigo. That's one of those weird colors, right? But indigo. Yeah. So this is the full spectrum. This is what we see from the sun. But you know what? The peak light from the sun, the peak, all right, the light that we get the most from the sun, if you look here, this is another curve, all right? And now those are wavelengths along the bottom. 350 this is actually this is wrong.
Ruh-roh.
Yeah, that wavelength, they should be swapped. Okay, so they got it wrong. That's amazing that somebody put out I actually borrowed this diagram. But just look at the green. Okay, you see the yellow and you see the green in there. Okay, the green is the peak wavelength that the sun is giving off. It kind of looks like yellow, but it's really yellowish green. Okay. But in that peak wavelength that the sun gives off, okay, you'll notice that all around it are other colors too. All right. So this is the spectrum that we get from the sun. You see the green section? That's actually a pretty hefty section. But we also get red, we get orange, we get yellow, we get blue, indigo, and violet. So the green is right in the middle of that spectrum. So if you're going to see green light, okay, you're also going to get all this other light. So that washes out any potential to see the green light itself coming from the sun.
Because all the other light's there, is what you're saying.
That is right. That other light is actually kind of preventing you from seeing this green light.
Even though there's a lot of green there, more than the others. Okay.
That's right. Yeah. So when we look at it, okay, we'll notice, for instance, that, and we call this Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet, right? Roy G. Biv.
Oh, yeah.
Okay. Red stars will have more than just red in their spectrum. They might have red, orange, and yellow, and maybe some green. Okay. Blue stars will have a lot of blue in their spectrum for sure. So you see the B, the I for indigo, and the violet, V. Okay. But you might also get some green in there as well. But you won't see much red. Just like with the red stars, you won't see much blue. Okay. And as we said, the sun actually peaks in the green. So again, with all the colors that are also coming in this continuous spectrum, we don't actually end up seeing at all. We don't see the green at all, So, yeah, but that's the reason, is because it's never just green. We don't just get green. We see red, orange, and yellow, and we see blue, indigo, and violet as well.
And what do those colors represent again?
The colors represent the continuous spectrum. If you break up the white light into its component colors, you see the rainbow in the sky. Water droplets are doing that for us. If you wanted to do it with a prism, a glass prism, we could do it with a prism, and we could actually watch the light form this rainbow, and that's the continuous spectrum.
Right.
So when we look at the continuous spectrum, it has to do with the different lengths of the wavelengths of the light. Short light is blue. Longer light is red. And green is kind of in the middle. But we get it on both sides. And when we get it on both sides, it makes it hard to see the green in the middle of all that. Okay. Now let's suppose we took out a green filter, a specific narrowband green filter that only looked at green light. Okay. We'd see a very bright sun.
Oh, interesting.
Because then we'd see the true green light that's there, but it's totally overwhelmed by all the other light that's around it. And then the green light is washed out by the red, orange, and yellow, and the blue, indigo, and violet light that we might see. And depending on the color of the star, it's shifted toward the red, or in the middle, or to the other side. And there's white stars too that do all of it.
So is maybe this isn't related, but the difference in the colors, like the white light, that is traveling at the speed of light. Are the other colors traveling at the speed of light as well, or do they travel slower because of their frequency?
No, they're traveling at the same speed. They're all 182,262 miles per second.
So light, no matter what color it is.
Yep.
Versus
light is light. Now you can get some strange effects, however, when these emissions are traveling long distance, especially in the radio frequencies from distant galaxies. We get something called a dispersion, and that's what happens when you get some of the wavelengths get sort of stretched out a little bit, and they arrive at slightly different times, and it has to do with the fact that over long distances, traveling in between galaxies, in fact, you might get some of that light impeded by things that other light is not affected by. So they can kind of outdistance each other, these different parts of the spectrum, and they get here at sort of different times. That dispersion actually is something that can help us figure out how far away something is and how far it came from. Yeah.
You can calculate that?
Yep.
Interesting.
The dispersion is a calculable data piece.
Cool.
Yeah.
So it's the dust that's dispersing
Yeah,
dispersing everything.
well, yeah, the dispersion can be related to dust or neutral hydrogen gas in between galaxies.
Oh,
Um,
interesting.
yeah, and um, I I don't have a diagram to illustrate how dispersion affects things from long distance, but keep in mind that we found out that fast radio bursts come from other galaxies because we noticed that these bursts had this dispersion applied to the spectrum that's arriving.
Mm,
Okay, and so when we caught them in the radio frequencies, um, we actually saw that it was spread out. And that dispersion is what showed us they were coming from very, very far, billions of light years away.
wow.
Yeah. So it's pretty cool, actually. You
It's
know,
amazing something can last that distance.
I
Or
know.
just something invisible can last that distance. So
I don't disagree. It's incredible. It really
it's
is
very
incredible.
cool.
Yeah.
Hmm.
Yeah. So um, now, when we talk about the stars in general, one of the things that we want to talk about are the different types of stars because they do some pretty cool things, right? Different stars, obviously, but as stars age, their colors can change. And what's color have to do with a star? Well, we've talked about color with stars before. And if a star is really, really hot, it's going to be very, very blue.
Right.
If it's not so hot, it's potentially white. And then as it gets cooler and cooler, it goes to yellow, to orange, to red. And red stars can be tiny stars, the size just a little bigger than Jupiter, or even at the size of Jupiter, as we found in a particular case. And or they could be giant red giants. Okay,
Mm,
it only has to do with temperature. These small
okay.
stars don't put out a lot of temperature, so their surfaces are about what we call 3,000 Kelvin, just a few thousand degrees Fahrenheit. But
Okay.
the supergiants, the really big ones, they might have been hot at one point, but once they expanded, the stuff out here is far from the source of the radiation in here.
Right.
So that energy is over time, over distance rather, is reduced, and you end up getting a smaller temperature at the outside. And those can actually be the same temperature as these tiny stars.
Hmm.
Okay. So
It was
we had to
hot.
come up with a different way to classify the stars, and that's because of that whole problem. So um, if we look at stars, we have to look at what they're doing to produce energy. Stars generally produce energy by fusion. They will crush hydrogen together and make helium. That's the initial thing that happens in a star. It's the initial way. It's one of the ways that stars survive, because when they push hydrogen together and make helium, which is the next element down the periodic table, then what they do is that process releases a ton of energy, and that pushes outward, holding the star up. So if it tries to collapse, it gets hotter and produces more energy, and so it stabilizes and ends up making an equilibrium called hydrostatic equilibrium, where all the pressure outward from the radiation is balanced by the gravity trying to crush it.
Right.
And that equilibrium lasts billions of years. Happily, we're in an equilibrium that will last another 5
Thank
billion years with
goodness.
our star. Okay.
And we know that
Yeah,
for
we do.
sure.
We do.
Okay.
We know that for sure.
Okay, good.
Yeah. Now, stars that are doing this hydrogen to helium fusion, when plotted on a temperature versus brightness scale, temperature versus brightness,
Okay.
we find that the stars will start at like the upper left and migrate down to the lower right on a snaky line.
Yeah.
And that became what's known as the main sequence. All stars doing hydrogen fusion into helium end up on this snaky line. Okay. And they have a Roman numeral called V of 5 for stars there. And the reason that the V is there, that 5, is because we have to differentiate between stars that are cool, like those little red giants. There's those little red stars down here, or
Okay.
down here rather, okay,
Right.
with those red giants, which are up here, that are big, 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 but the same temperature. So the 5, that V, is a luminosity class. The
Okay.
spectral class is the color, and the luminosity class is effectively the size based on the brightness of the object, how big it actually is in real life. That's something that's really important. So when you put all that stuff together, it makes a diagram like this. This is the Hertzsprung-Russell diagram. And if you look, okay, at the top up there, you see the big hot blue stars. These are the O-type stars. You look down the bottom, you can see that O at the left. They're the hottest and the bluest of stars. And you look up there, and there they are. They could be up to 60 times the mass of the sun.
Wow.
Which ain't hay. And then down in the middle, right here at 1, okay, look straight across, there's the sun. Okay.
Right.
And the sun is a G-type star. We're right in the middle of the yellow there. And the G-type stars, and with a luminosity class of 1, that means that the star is on the main sequence because it's converting hydrogen into helium. The main sequence is that snaky line we're looking at, going from up here all the way down to down there at the lower right. Okay. And so that's the main sequence. But then to the upper right up there, you can see the realm of the supergiants and the giants. Wait a minute.
Supergiant.
Yeah. And it's all temperature. The placement here on the scale, left to right, is based on temperature. Nothing more. Okay. And so the scale here, on the other hand, on this side, is based on intrinsic brightness. Okay. And that relates to the size of the star. All right. So the bigger stars that are giant or supergiant stars could be O stars. But there's a problem, because stars that are that hot and young, they burn through all their hydrogen very quickly. And they quickly go off that main sequence and end up down, or moving up rather, to expand into a supergiant briefly. But as they do that, they're going to move across the diagram and go into the red area. Right. And they'll be cooler on the outer edges. Okay. Give you an example. Okay. The star Betelgeuse in Orion used to be right here. It used to be a big, bright O star up there at the top left. But now Betelgeuse is all the way on the other side of the diagram. Wow. And you can see it labeled up there. You see it labeled up there, Betelgeuse.
Yep. Top right.
Okay? Top right. And Betelgeuse went from being this O star at the top left to being this supergiant red star. So as it expanded, what happens is, as it expands, it moves, that the outer layers move farther and farther away from that hot core that's producing incredible amounts of energy. And so it reduces temperature. And so it ends up dropping in temperature. So Betelgeuse is very cool on the outside, but its core is still furiously going. And it may already have gone supernova, but it's definitely a supernova candidate. And not just a candidate, it's guaranteed that it's going to explode.
Oh, I hope we can see it. I hope it's exploded already, so we'll see it soon.
Yeah, I hope it exploded 749 years ago.
Exactly.
Because it's about 750 light years away. And that light train is going to just reach us at some point. I wish we could do instant transport to different locations. Wouldn't that be cool?
Well, it's going to be kind of like that if you're talking like that warp drive to get places. I mean, maybe not instant, but pretty darn quick. So,
and not even the warp drive, but the dimensional drive. If we can use the dimensional shift, and she's referring to a talk I do around the country, which is very popular, which shows a lot of interesting relations. Even Avi Loeb at Harvard's talking about it, and this is a interdimensional travel mechanism that would take alien beings out of a 4 dimensions, X, Y, and Z, moving through time, and go into a 5th dimension here, where they could travel literally from one position in this 4-dimensional space, like where we are sitting in our chairs, go into this area here, the 5th dimension, not the band, okay, the 5th dimension, and then pop back in at a totally separate 4-dimensional spot, because they travel outside the universe of our known space, I should say, using this method, and they can pop back in. And that's really, really a shortcut to what we talked about. But think of your hand, 4 dimensions, 5 dimensions, like that. Okay. The 5th dimension, okay, is not subject to light speed barriers. In fact, the universe shrinks the farther in you go. So you literally, it works like this. If you travel 12 inches in here, the 4 dimensions, you go 12 inches. Okay. But if you move into the 5th dimension, if you go in just a little bit and travel 12 inches, then when you come out, into the 4 dimensions, that 12 inches might have gotten you to the moon. Okay, depending on how far you go in, or maybe it got you 10 feet. Okay, but if you travel 12 inches in this 5th dimension, but you go way far into this 5th dimension, which is really warped, the universe is really compressed, that same 12 inches when you come out could correspond potentially to the distance to Pluto, as an example. So, and there's any scale is doable in there. So with this particular technique, we could get to Alpha Centauri not in the 10 or 12,000 years it would take us now at the fastest possible speed we can move, but 20 minutes. That interdimensional travel mechanism will open up the universe for us. So when she mentioned getting somewhere almost instantly, that's about the best we can do. But that's interesting because we could go 750 light years to Betelgeuse location, or a little bit back in case it's already blown up, and show up there. And maybe it might take us 2 hours to get there.
Wow.
Okay. That's like driving Connecticut to Boston. All right, I'll do it.
Do you think there's
750 light years away?
Do you think there's going to be a lot of volunteer test pilots to practice interdimensional travel?
I don't think they're going to have any shortage of people.
You don't think so? I mean, the risks to do it the first time, and how far in do you go, and where are you going, and what happens if you run out of gas before you come back? So,
well, that's the thing. You don't really need fuel. That's the whole point of this, because if you notice when people talk about UFOs, they tend to be round. Okay. And that roundness shows us something really, really important. If we look at the shape of these objects, that gives a clue as to how they operate. Right? The shape being round means that most likely they're generating particles in a circular ring, like we do now. A particle accelerator. You got it.
Yeah.
So these are particle accelerators.
It's small. Theirs is small.
Yes. Theirs is a 30-foot ring. We have miles and miles of a ring because we're not there yet. But if you think about it, their interest in us could very well be, hey, these people, they're coming up on a potential technology. They might demand a piece of our action someday. You know, and on that note, I'm sure we'll be back to talk about that more. Yeah, I think we're ready now, taking a break now, aren't we?
Perfect time.
Right.
Yeah.
We'll
okay.
Be back right after this.
Hey members, the new KGRA DB app is now available on iOS and Android devices. Gain on-demand access to any KGRA DB programming. Download any show directly to your mobile device to listen or watch on the go. Go to the App Store and search KGRA DB.
As UFO reports come in from around the world, the Mutual UFO Network, MUFON, is there. We continue to explore new cases and build our massive database. We share our information with the world in a number of ways. If you would like to be part of our investigative team, you are always welcome. What could be more exciting than exploring the UFO question firsthand? Join MUFON, find your friends.
You're listening to the KGRA Digital Broadcasting Network. We provide unparalleled coverage of trending news in the world of ufology, cryptozoology, and paranormal phenomenon. Whether you're watching our video live stream or listening to one of our audio programs, you are getting the best from world-renowned researchers and hosts, guiding you through topics the mainstream won't touch. Miss one of your favorite programs? No problem. Head over to the members area at kgradb.com for access to our massive library of award-winning content. Make contact, stay connected, only at kgradb.com.
Hey, Beck. We're back.
Hello.
We're back. Hi. Hi, guys. How
Are you gone?
Yes, I have to put my brain back in. Hold on. There we are. So I want to thank all the people in the chat. They're very kind, very nice comments out there. So I think that it's important as we're going through these discussions of stars. We talked about, obviously, that Hertzsprung-Russell diagram here, which talks about fusion and so forth. But something that's interesting about these stars is that when we talk about stars, I want to make it clear. You look at the sun, you got this big bright ball in the sky.
Right.
It's almost 865,000 miles in diameter, point to point. Okay, massive. But that's not where the fusion is taking place. The energy being generated is in the core. That outer area is called the envelope, and that's just along for the ride. That consists of hydrogen, and in our sun's case, there are hundreds of other elements that were made, 100 or more elements that were made previously to the time the sun existed. And the sun just gathered them up when it made itself at that point in early solar nebula. Okay. Now we have like 118 elements in our periodic table, and we've got, several tens of actual elements in our Fraunhofer spectrum, the spectrum that our sun has. And when we look at the spectrum, it looks a certain way. We can determine what's in the star by looking at the spectrum. And we're not talking about just looking at this thing. This is a spectrum. But that's not the actual spectrum of the sun. The spectrum of the sun shows these various lines, which we're going to talk about in a minute. But the core of the star is the only place where energy is being generated. All right, and it's only in there that nucleosynthesis is occurring, hydrogen being converted into helium in our case. All right, so the sun fuses the hydrogen to helium, and as it gets older, it may fuse helium into carbon for a time.
Right.
But only that core is doing it. The rest of the star, as I said, just along for the ride, we call that the outer envelope.
And how big is that core?
That core is actually a good question. The core is about, in our case, 86,000 miles in diameter.
Oh.
Yeah.
That's pretty small. I mean,
it is. It's actually the size of Jupiter. Okay, so it's the size of Jupiter inside now.
Big.
Smaller stars have a smaller core, right?
Okay.
Bigger stars have a bigger core, right? But the thing that's important is when you have a core like that, the reason it's doing fusion at all is because that outer envelope around it, that's a lot of mass. And gravity is all operating on the center. So as it operates on the center, there's a high compression force. And there's a high temperature rise every time it does that. So it's high pressure, high temperature, okay, in a relatively small volume. So what happens is the temperature rises immeasurably. And once it reaches around 15 million Celsius, hydrogen fusion can occur. And when you get to a star about 864,000 miles across, the density in the core rises up to enough of a dense nature that you'll be able to start fusion. Now, when I say density, what's the density, right? I'll give you a comparison.
Okay.
The core of the star, like the sun, as we mentioned, 86,000 miles in diameter. The density is 150 grams per cubic centimeter. That's a cubic centimeter, centimeter by centimeter by centimeter. So it's 150 grams per cubic centimeter. Now, as an example, okay, if you convert that to pounds, that's a third of a pound. Doesn't sound very impressive. But consider now that lead, okay, the density of lead is 11.5 grams per cubic centimeter. And you know how heavy lead is, right?
Mm-hmm.
Yeah. So
Yeah.
11.35 grams per cubic centimeter. That's how much lead is. And we're talking 150 grams per cubic centimeter in the middle of the sun.
Cool.
And only of protons, not atoms of Pb, which is lead. Okay. So now you can see the compression is active in there, and we're getting a lot of heat down there. Another comparison, density of water is 1 gram per cubic centimeter.
Oh.
Okay.
Yeah.
Right. And water, you can push your fingers through it and all that. You can't put your fingers through lead, which is 11.3 grams per cubic centimeter in density. So do you think you could put your hands through the center of the sun? If you could somehow do that at 150 grams per cubic centimeter?
Probably not.
Probably not. So you see, a lot's going on down there. Yeah, so the density is incredible. And that's why we get fusion at all, right? Because it's high density, high pressure, and high temperature that results. Now, the temperature in that core can change. What happens many times is when the star is going through nuclear fusion, it's converting hydrogen into helium. It's pushing out with the same amount of force. Okay. However, when hydrogen fusion tapers off, as the star runs out of hydrogen, well, the star begins to collapse because gravity now is winning out over the balancing act that it's going on with outward radiation pressure, gravitational force. So as it comes down like this, the core begins to contract. And as the core contracts, the density increases, right?
Right.
And what increases after that?
Is it the gravity or the temperature you're saying?
Yes, the temperature increases. And thus now a core that's now full of, say, helium can get hot enough to, say, over 100 million Celsius, from 15 million Celsius to do hydrogen into helium, and start turning helium into carbon. Okay? So as that happens, as the core contracts, it gets much hotter, and the emission, the radiation pushing out, is now getting stronger with the helium burning, and the star begins to increase in size tremendously, and that takes it up to the red giant stage. It's signaling the end of the life of the star, and it has a few 100,000 years or so before it may go.
Mm-hmm.
All right. And so we're looking at a condition then where it's a balancing act until the hydrogen runs out, and then the star's core begins to collapse in there, pushes those outer layers out. All right. But then when the helium runs out, the star begins to collapse again. And when it gets down far enough, it could actually start to take carbon and fuse it into nitrogen and oxygen. And okay. And when that happens, it does this thing again. Mm-hmm. Right. Well, in the small red dwarfs side, the ones at the bottom of this diagram here on the Hertzsprung-Russell diagram that we talked about, okay, down in the lower right there, those stars are so small that when they get large, they're probably just going to contract down and become little white dwarfs. Okay, that's their life. But because they're so small, I call them little tiny percolators in the universe. They're little percolators.
Going back and forth?
No, because not a single one of these M stars has died since the beginning of the universe.
Oh.
They live trillions of years.
They just change.
See, there's a lot of things that goes on in these stars, Tara, that's really cool.
Mm-hmm.
They have the hydrogen envelope, right? And and they have that core, okay, which is much smaller, the size of a planet like Earth or something maybe, and it's causing hydrogen fusion. However, because of the nature of the star, because it's so small, the stars have a convective region, all right, and a radiative region. And sometimes right outside the core that we have a radiative region where the radiation is pushing out. And then out or further from that, there's a convective region where stuff kind of boils like a pot on a stove. Okay. Well, when you have a small red star, almost the whole star is convective. And that's taking hydrogen from outside down back into the core. All right. And giving it more fusion fuel. And so the star can continue to percolate for trillions of years.
Cool.
So talk about a star that could possibly give way to life eventually. There's more of these red stars out there than any other kind. So it's possible that if we're going to find life, it might exist around a planet that's orbiting a red star. You know, a small red dwarf, as they call it.
So we don't have to look just like at a G star or anything for
no,
what we might need.
No, we might find life around these red dwarf stars, you know, which are really cool. Now, the thing that's interesting is I talked about that envelope and what stars are made of, and inside the star, the core, like I said, is the only thing doing nuclear fusion, and then the envelope's along for the ride. In that envelope is all the stuff that the star was made with, and fusion creates new elements. Hydrogen is made into helium. Okay, helium in the later stages of the star's existence, helium is made potentially into carbon. Right, that's where our star will go. It will only go from hydrogen to carbon eventually. It's never going to get much further than that at all. It doesn't have the mass to do it. But you know, I showed you stars on that diagram. If you look in the upper left here, okay, there's stars that are 60 times the mass of our star, and 30 times, and 20 times, and 10 stars. Spica is 10 times the mass of our sun.
Wow.
Okay, and it's a very, very hot, B star that we see there. Now, the thing about these stars is that the bigger and hotter they are, the farther along in that fusion process they can go. Our star is not really that massive, so we can go from making hydrogen into helium and helium into carbon, right? Maybe some oxygen isotopes, okay? Stars like the Spica and these other hot blue stars, well, they can go right past all that and go all the way to iron, number 26 in the periodic table, okay? Now, that's pretty impressive because these stars will make all these elements, right, all the way up to iron, and those are really impressive. And this is an example of the table.
Look at all of those. Oh,
yeah. If you look at the green, okay, those are dying low mass stars. So dying low mass stars, there's a process that can actually allow those elements to be built. Okay, this is our periodic table, right? I'm showing we're going up to 103 in this one. We're up to 118 now. But once a star explodes, these massive stars explode. You see number 26, iron, kind of in the center of the diagram there. Okay.
Phi.
Yeah, Phi, Co, Ni, Q. I mean,
Q's-in.
right. Cobalt, nickel, copper. So once you reach iron, these big stars can't go past that because everything before this, every element made before this in a star, okay, ours, like you look at the top left, hydrogen goes into helium at the top right underneath the KGRA logo, okay? And then you can get lithium, beryllium, and boron, okay? But then you get carbon, nitrogen, and some oxygen. And what happens is these elements are made in that nucleosynthesis, the fusion process. However, once the massive stars get to iron, okay, there's a problem. Every one of the previous processes liberates more energy than goes into it. All right. So, for instance, to make titanium, Ti, okay, when an element like titanium is made, or calcium, or potassium, before it, K is potassium, Ca calcium. Okay. When you look at elements like that, more energy is released by building a titanium atom or titanium nucleus than it takes to actually make the titanium nucleus. So more energy gets released from the process. By the time you get to iron, it goes over the top of the curve, meaning to make anything past iron, you actually have to put more energy in. And so naturally a star won't go there because it does what's easiest, and what's easiest is to get to iron. It can't go beyond that. So how do all these other elements come into being? Well, they come into being through exploding stars, as you can see in the yellow. Okay, they come into being through merging neutron stars, which are the purple. Okay, they come into being through dying low mass stars, which are in the green. Now, there are processes that occur in stars like our sun. All right, and in our sun, we actually have these process that takes place. It's called the slow process, okay, the S process, and it's something called a neutron capture process, where every once in a great while, a neutron gets captured into the nucleus of one of these nuclei that's being made in the sun, okay, like a helium atom or whatever. And then what can happen is you can actually get that neutron to be converted into a proton. So if you have a helium nucleus in the sun, it could magically capture a neutron. It's certainly not magic. We know the process well.
Ta-da!
Exactly. Look behind that curtain. Okay? And it's bright. Okay. And so that neutron can get spontaneously made into a proton. And now you don't have a helium atom anymore. You might have a next atom down the line, lithium or beryllium, and then that could further decay to, say, a carbon atom down the line. So this process is it's slow because it takes a long time to occur, but over billions of years, a significant amount of that stuff can build up. All right.
Yeah.
So, but that's only happening in the core. That's not happening in the envelope. The envelope, again, is just up for the ride. So when we look at the sun's spectrum, we see an interesting set of elements that appear in the sun's spectrum. Almost all of those are elements that the star was made with, and they're just along for the ride. Now it's all plasma, meaning that it's no longer an atom. An atom has a proton or a proton with neutrons, and then electrons circling them.
Right.
Okay? Well, if you get rid of the electrons, then all you have is protons and neutrons in there. Okay. And protons, like I said, protons and neutrons is all that would be in the nucleus. And those represent plasma, singular, proton neutron bundles and electrons. Separately, we call those plasma because high temperatures required to achieve a plasma state. And that's what we've got in the envelope of the star. All right.
And you said that all the elements are within that envelope. Are they all released? Are they all?
Well, that's a very good question. Okay. What we look at when we look at stars, okay, we see, for instance, that, and I'll just go right to this because I think it probably makes sense. If we consider what's that?
Hopefully it'll make sense.
It will. Okay. Let's talk about how we see what's going on in a star. Okay. And basically it comes down to this diagram. All right. We see the continuous spectrum, which we saw right here. Okay.
Right.
Right. And then we see this. Now, the continuous spectrum is up there on the top. If we're just looking at the star directly, then we're going to see that right there. We're going to see the continuous spectrum of the star. Right. And that star right there, we view it from that point of view. We're just going to see that continuous spectrum. That's what we see with our sun, right?
Mm-hmm.
However, if we're looking at the sun through a cooler gas, then we're going to see dark lines in the spectrum. Now, that cooler gas is not constrained to be like a cloud out in front of the star. It could be the outer envelope around the core of a star.
Okay.
And so we're looking at the dark lines called absorption lines. What are those? Well, the gas itself, with all of the many atoms it could be composed of, is absorbing some of the energy. from that hot source beyond it. Okay, and when that hot source reaches the gas, all the different gas nuclei that are out there absorb a little of the radiation, and they make these dark lines, an absence of that particular frequency. Because we look at a spectrum, and it's a frequency. And we measure it in nanometers. Okay, from one end to the other, the spectrum is going to be a set of nanometers. In the visual spectrum, it's like 300 or 400 to about 700 nanometers is the visual spectrum. And then we got past 700, we're into infrared, microwave, and radio frequencies. And if we go down below the blue, okay, that we can see it goes down into the 300, and to the left of that is the ultraviolet and the gamma ray, cosmic ray range, X-ray range. Okay, and again, only the visible light source is the stuff that we can see here. That's the only stuff we see is the visible light. Okay. So when we look at a spectrum when we look at a spectrum of light that's going through a gas, in other words, the core of the star sending out energy that goes through the outer envelope of the star, we see these dark lines. These dark lines are in a specific place in the spectrum, and that specific place is determined by the element. Each element has a different location in the spectrum, and we know it well. Okay.
Perfect.
Yeah. And so now, if we're not looking at this gas through a star, let's say we're looking at a star that is a bright, hot star that's causing a nebula to glow. We're not looking at a star directly, but looking at now a nebula. Well, now when we look at the nebula, we're going to see that same gas that shows us the absorption spectrum, if we're looking at it in a star, is going to show us an emission spectrum, bright lines. It's called a bright line spectrum. And guess what? Those lines are in the same place as the absorption spectrum, but they're actually now bright lines in the spectrum.
Instead of black. Okay.
That's right. Why? Because the gas is actually emitting light, all right? Because it's actually absorbing gas, which gives you a dark line when you're looking at it against a much hotter background source. And it's emitting light when it's out there all alone. All right. And that emission of light is because it's absorbing energy and then re-radiating it. All right. Absorbing energy, we'll see a dark line. All right. And that's when it's in the star's envelope. But if it's a gas cloud around a hot star, then we'll see these bright lines of emission. And this is called an absorption spectrum, and this is called an emission spectrum down here. So absorption and emission. And that's what we see in the universe, absorption and emission. Now, another way to look at it is like this. Okay, if you look at a light bulb, all right, you just see a continuous spectrum. But if you actually have a hot gas that's lit up or powered by a star, and it's in the envelope, well, then you'll see an emission spectrum. This is an actual emission spectrum here that you see. Okay. And the lines are the color of where they are in the spectrum. Okay. All right. And so that works like that. Now, this whole thing about hot gas and cold gas, those could be the same gas. Okay. It basically just means relatively cold. All right. So that same star, all right, if you had the envelope of the star, you'd see dark lines in the spectrum. All right. But if you could have a separate gas that was just near the star and not in the same, didn't have that bright hot star behind it, they had the contrast basically, then we wouldn't see the absorption spectrum. We'd see the emission of the gas itself. Okay.
Now, Mark, do you have to have different? I mean, this sounds like a silly question. Do you have to have different equipment to check the emission and the absorption, right? Or do you just look at it and see what it shows you?
Oh, that's an excellent question, because when we look at it with our telescope, we just see the visual spectrum. We see the color, right?
Right.
And so we're looking at emission of, say, the Lagoon Nebula, or of the supernova remnant. This reddish orange that we're seeing in here, this is hydrogen gas emitting red light. It's 6,500 656.3 nanometers, or 6,563 angstroms if you're still in that old unit. Okay, but
Huh?
I know the emission that's in the red end of the spectrum, in other words. And when you see like a bright star, now actually this is from a supernova remnant, and the supernova occurred right about here. And you can't see my cursor.
Right in the center, though, right?
Yeah, right in the center. Yeah, and it's a little bit to the lower right of the center because the supernova process pushed the whole core of the star in a movement, so it started moving it.
Oh.
But the bottom line is that red is due to hydrogen emission. Now, if that was still in the envelope of the star, we'd see absorption lines from the hydrogen gas. Okay, but we see emission because it's now a separate gas glowing on its own. When we see a sunspot, it looks black against the sun. That's because what's behind it is much, much hotter than the sunspot by a couple thousand degrees. If the sunspot was removed from the sun, it would glow red by itself.
Right.
And you'd say, wow, that's the same spot? Yes, it is. Because now you don't have the contrast of a much brighter sun behind it. You just have that little spot all by itself. But it would glow red hot.
Right.
Because that's how hot it is. Right? So in the same way, the envelope of the star, around the star, is going to have the absorption lines because the much more distant hot core of the star is going through relatively cool gas that's not millions of degrees but thousands of degrees, and so it can still absorb energy. If we could slough off that outer envelope of the star, however, then the gas, if heated up by that central star core remnant, we might actually see emission from the nebula, and that's exactly what we do. So these emission lines form when the gas, without that bright light source, such as a star or in a nebula, is in a nebula, and it's receiving stellar radiation, but not directly like from the star, from our perspective. Okay. Now, as an example, I'll show you this absorption spectrum for different types of stars. Yeah, I know. And if you look at the top here, up there is an O star, and down there is an M star. Notice the difference in the lines. See what I'm saying? These lines, these different absorption lines, tell us about different things that are in this atmosphere of the star. And you might also notice across the top that there's something written there. Well, those are the elements that we see. Okay, and starting at the top right, we see helium-1. Well, you don't see helium that much until we go down further to the M stars. And now we see that there's helium that it was made with. Okay, then if we look just to the left, that's hydrogen alpha. That says HA. I know it doesn't look like an A. And you notice that the lines get bigger and bigger and bigger until we reach this A0. A0, again, OBAF, GKM, those are our spectral types, and they go from O0 to O9, B0 to B9, A0 to A9. So A0 is like the quintessential, point where if we have a star that's an A0, which is Vega, the star Vega, which is overhead right now in the summer sky at night at 9 o'clock, Vega as an A0 has the strongest hydrogen lines of any part of the spectrum, or any stellar type. So you see on the left in the red, you have H alpha at the top, and you move over and you'll see the next brightest dark line is H beta, and then H gamma is the next one. And you'll notice that all you see are the dark lines. You don't even see many other lines in the spectrum, right? So we'll see that we have we have hydrogen beta, we have hydrogen gamma, hydrogen delta, that looks like a little S up there, okay? And so we have that spectrum of the star, and that's taken with a spectroscopic system, a spectroscope, all right? And then you get down to the M stars, and now you're looking, why are there so many lines in those M stars at the bottom? Well, the reason is because those M stars are not hot on the outer surface. So what happens is we see the spectrum of the outer surface effectively. And out in that outer surface, we can see that we have things like titanium oxide. Wait a minute, that's a molecule. So on the lower right in the red on the M2 star there, which is down here, okay, M2, and the far right, you'll see Ti and then a big O. that's titanium oxide. And that's a molecule, right? And there's several of those there on the right side, titanium oxide. Okay. We have iron. Okay. And we have sodium. All right. And there's more of these molecules. All right. And the reason is because when we look at a red star, the outer layers of that star are so much less hot that they can actually allow molecules to form in that outer atmosphere.
Huh.
Right? Yeah. So that's kind of interesting. Now, what we're going to be doing with the Benson telescope, we're still going to be, showing beautiful things like this and so forth. That's not going to stop. But we're also going to be able to do things like this. Okay.
Ooh.
These are different stars. Okay. Up here at the upper left, you see we have Delta 1 Lyra, and it's a B2.5 star. Okay. Then we have Gamma Lyra right here, which is a B9 star. But you notice it has that luminosity class after it. So B2.5V means it's fusing hydrogen into helium. B93 means, however, that this is actually a giant star. All right. And then we have the A05 for Vega. And you can see those hydrogen lines are the big, broad, dark lines.
Oh, yeah.
Yeah. Then we have Zeta Lyra and Zeta Lyra. And you notice that this is an A4 star. So the lines are getting fainter, but we're starting to see more other elements in the spectrum show up quite visibly. Okay. Then we get down to here, and you'll see that the K0 star, that's an orange star. And we see there's a lot of lines in there of other elements. Delta 2 Lyra, okay, that one's got an incredibly crazy spectrum, but then again, it's also not a V. It's actually a type 2, which is a giant. And at the bottom, we have an M star. And those broad bands represent molecules that are in this spectrum. So you see, depending on the M53 actually is a giant with molecules in the outer atmosphere. These images were all taken with what's called, if you look at the top, it says Star Analyzer 100. That's exactly what we have in our other telescope that we're putting out there, along with a nice special camera which tunes everything properly. So we'll be able to get exactly these spectra. So we'll be able to go through and look at nebulae. Now, when you look at a nebula, okay, remember I talked about this diagram when we say, well, if you saw the hot source, and we saw the envelope of the star, which is where the word gas is over here, okay,
Right.
then you'd see the absorption spectrum, all right? But if you looked at the gas from a different location, from a different perspective, other than looking through at the bright hot star, you might see that it has these emission lines, and they're going to be in the same place as the absorption lines. All right.
Okay.
So that said, now let's take a look at this. This is an actual spectrum
Ooh.
of Messier 57, the Ring Nebula.
Pretty.
Those lines represent the sample zone. Okay. At the top, up here, that right there that you see right up here, that's actually the actual spectrum of the star.
Wow.
Okay, of the planetary nebula. Okay, and then down here you see the actual intensities. Here and along the bottom you see the wavelength of this material, and what you're looking at then is the bluer end, not the end where the hydrogen alpha is. That's in the 65 or 656 range, a nanometer, and so that's actually a little bit to the left in this scale. We're not. It's out here more.
Okay.
Out there
Yeah.
more. Okay, but you'll notice that we have right here. We have oxygen 3. That is a doubly ionized oxygen, and we have lines of it here. Oxygen 3 is the color as you see down here. It's in the 400 plus angstrom range. I'm sorry, 400 nanometer range from here. And you'll notice that in the nebula, visually, you'll see a little green. Well, that green is actually the oxygen 3. Okay? Because that's where we can see the green. We can see the green when it's in a nebula. It's being excited by the hot central star. All right.
Right.
And then you go further on down this line here. All right. And you're seeing we've got lines of mercury and helium-2.
Ooh.
And there's more. So there's some hydrogen out there as well. But if you think about it, that's actually pretty incredible. So we're going to be able to take spectra like this. This spectrum we're seeing here, this is a spectrum of a planetary nebula, right? Now, and when the star's life ends, right, and all the elements that it could possibly make are made corresponding to this diagram in the green parts, dying low mass stars, which corresponds to what the ring star used to be. Okay, then it's going to populate its core with some of this material. And so if we did a spectrum of the white dwarf, which is in the middle, the white dwarf's about the size of the planet Earth. Okay, if we did a spectrum of that, we'd find that it had some really interesting elements. We'd see carbon, we'd see oxygen. Okay, but we'd also in the envelope, that envelope that's spewed, what's coming out is the former envelope of the star, not really the much of the core. The core stays with the white dwarf. Some of that core is ejected, but we're seeing mostly just the material that the star was made with. So we're seeing the oxygen that may or may not have been created by the star. Some of that was made with the star. We're seeing argon in there. There was argon in there, which you didn't see, but argon was made with the star for sure. And so it shows up now in this nebula of expanding debris coming out from the remains. So you see, we're taking a little bit of a deeper view into this, I realize. But I think it's kind of important to understand how stars develop, how their formation evolves over time, and that's the kind of thing that we're doing, you know. So once again, this diagram here, this illustrates exactly what we'll get with our telescope. We'll be able to see these lines in a star, and this will tell us a lot of details about the star. So we could, for instance, take an image of T Cor Bor, T Corona Borealis, which is going to go nova. Okay, and if Benson is up and running in time, we can get a spectrum of it, and we'll see potentially some absorption lines, but we're going to start to see emission lines too showing up.
Cool.
And that's going to be from the nova expanding out from the star, and it might take a couple months for those to really manifest to see them, but they'll be there, and we'll be able to see them, and that's the coolest part, you know.
Right.
Yeah.
So
yeah, go ahead.
Well, I was just thinking, it's probably not related to, but you're talking about the red stars and everything, and then you talked about the blue star there. Something that's totally different, but is also confusing because of the colors, is the shift in, are they traveling towards us or away from us?
Oh yeah, the Doppler effect of the stars. And let me complicate matters for you. Every star is moving toward us or away from us to some degree. Very rarely is it going directly alongside us. So if it's coming toward us, then the light will be shifted more toward the blue. But you know what that means? It means that all the spectral features, all the spectral lines that we see here, okay, like for instance, if we were looking at hydrogen alpha, which let's see if we can go here. Okay, hydrogen alpha in the upper right there, you see that series of dark lines in the different types of stars?
Yes.
Let's go to the A0 star right here.
Okay.
Go across the line all the way to the end. You see hydrogen alpha. That's the bright dark line. Well, if that star was coming toward us, then all the lines we see in here might be shifted a little bit leftward toward the blue. So all the lines would be shifted into the blue a little bit. That's called blue shift. Okay. And if the star was racing away from us at a high speed, all those lines would be shifted a little bit, well, that way. They'd be shifted toward the red. Okay, so it would all be shifted. And that's the complication. Okay, if you know a star's motion through space, you can develop a factor to compensate for whether the star is coming toward us or away from us.
Okay.
So when you look at a spectrum, and there have been times when we had to figure this out. When I was getting my degree, we were analyzing stellar spectra. There were times when the star would be coming toward us, and H alpha didn't line up, H beta didn't line up. It's because it was being blue shifted as the star was moving toward us. And once you compensate for that, the lines shift to where they belong, and you get a normalized proper spectrum. Okay. So that happens. And the other thing too that's interesting, okay, when we look at these spectra here, okay, some of these lines look nice and sharp, right? Like again, go to the A0 right here. Okay, at A0, you can see these A0 lines are pretty sharply defined.
Mm-hmm.
But you know something, they didn't have to be. That's another wrinkle. If the star was a rapid rotator, and there are stars that are rapidly rotating, then those lines get broadened. Okay, and that line broadening is the result in some cases of the star rapidly spinning. So that could confuse things too, because sometimes the lines that you see are very close together. Like if you have a rapid rotating star, it's okay, for instance, we'll say the A0 like here. But what about when you get down to like the K5? Well, now all those many lines you see near the middle of the spectrum,
Right.
they might be broadened into each other, creating just a band of dark, and line broadening is a problem we have to face and try and figure out too. So the rotation of a star affects the spectrum. The direction of the star's motion affects the spectrum. Okay.
Yeah.
The temperature of the star affects the spectrum, So, and the state of the star affects the spectrum. So there's a lot of things that matter, you see?
Well, and then how do you know you have the right data? Is because you're taking all of that and putting them together?
Absolutely. You have
versus
to take
one.
Right. I can't just look at one spectrum that we create here. Let's say we did one of Alpha Lyrae here, again, Vega. Okay. Let's say we did that spectrum. This one spectrum of Alpha Lyrae is not enough to make a determination of everything that's going on. We have to know which direction the star is moving and calculate the right locations for all those lines, because we could misidentify lines that are close together.
Right.
They could be shifted over enough to say, wow, that iron line wouldn't be in Lyra, but the calcium line is really, too bright. That's because you're looking at the wrong line. If you shift it to the right a little bit, now the calcium line comes in. Of course, I say that, but calcium lines typically are actually quite bright. There's H and K lines, two lines of calcium in the star spectrum that are quite bright. In our sun, they're quite bright. Let's see here. If we're looking in here, you can see a bright line between 5,000 and 6,000. You'll see a label along the bottom that says calcium 1 and iron 1. And that's a fairly bright line. You see it?
Kind of in the turquoise-ish color.
Yeah, that's right. And thank you. The turquoise color. And it's a bright, dark line. Okay. And there's multiple lines that you'll see. Notice how bright sodium is. Okay. Sodium really shows up in these M2s, and they're less so in the M0s right above it and the K5s.
Yeah.
Okay. Finally, it's non-existent by the time you get to the A5. But from the late F all the way down, you see them. And
that's really cool.
It is. And so stars are element factories. They're building elements. They're made with elements. And the stars that exist now are stars that are young, right? The younger stars that we see that are the bluer stars. But when we look at older stars, we'll find many times that they're metal poor. What's that mean? What's a metal? We look at the periodic table. I'll bring up that ugly table one more time to shock people from their. Okay. All right. You have hydrogen on the left, and you have KGRA on the right. Oh no, wait. Under KGRA is helium. Okay. You have helium on the left, hydrogen on the left, helium on the right. Everything after them are what we call metals. Yeah, I know that's stupid. It's not true. We're calling gases metals. It just means that that hydrogen and helium were the original elements in the universe that were formed, and everything else after that was created by nucleosynthesis, other than some lithium and some beryllium. Okay, all that stuff was made originally in the universe, so everything else is not. All right, it was made by some stellar process. Okay, so population 1 stars are generally younger stars, like,
Which is still old, right?
oh, of course, yeah, they're billions of years old.
Yeah.
Okay, potentially. However, they are stars that are in the disk of the galaxy, and they include most of the O stars, which are young and hot, B stars, also young and hot, and A stars, some of which are young and hot. Okay, now they will be in age, on average, these stars, a few million to 100 million years old, and that's their life expectancy. They aren't going to live much longer than that. Yeah, the A stars can live longer than that. The O stars are a few tens of millions of years. The B stars, maybe a 100 million years, a little more. A stars, more than that. G stars are up in the billions, right? F stars are slightly less because they're a little warmer, hotter, go through their hydrogen faster. So from the top of that Hertzsprung-Russell diagram that I showed before, all the way down to the lower right, okay, those stars that we saw are stars that are actually longer and longer lived as we move down. Okay, down the string, down the middle part. Okay, upper left, all right, upper left to lower right along that snaky line, youngest and shortest lived to longest and oldest, effectively, oldest lived. So those are what we'll see down there. The redder they are, and the smaller they are, the longer they'll live. All right. So that's how that works. It's actually pretty cool. Now, so population 1 stars are not those red dwarfs that we see. The population 1s are the bluer, the OB and the A's. Okay. And the population 2 stars are the ones that we'll find in many times in globular clusters. And how do we know? Well,
how do we know?
We know because we examine their spectra. And so when we look at these stars, we look in their spectra, and we see that the stars, okay, in the spectra of the stars that are in globular clusters, they don't have very many lines at all in them. And that means they weren't made with very many elements, which means there weren't many elements available to them to be made with, which means they were made very early in the universe's history.
Oh, interesting. Okay.
So we look at a globular cluster like Messier 13, okay, or Messier 5, or Messier 22, or Omega Centauri, which we haven't seen yet, but we'll see from Benson.
Cool.
These globular clusters have sometimes millions of stars in them as a globular cluster.
Wow.
It's possible that they're bound by a black hole in the center, which is why they may exist at all. That's another set of studies. But the fact is, these globular clusters don't have anything much beyond hydrogen and helium. So what's that tell us as exoplanet hunters? It tells us, as you might guess, we're probably not going to find a lot of life in a globular cluster. Yeah. Now, they're halo objects. They go plunging through the disk of our galaxy and then back out, and they keep going around. Some are outside all of that. Okay. But for the most part, they're plunging through the disk. And it's possible they could shed a few stars. They get sucked off by other gravitational forces, or they might acquire some stars. If they pass near enough, that whole cluster of stars might drag a star down with them as it goes through, and that becomes part of that cluster, perhaps. So there's a possibility that can happen. That said, that's one way in which we might find a globular cluster planet out there that it might have actual potential for even being in existence. Because without hydrogen or helium and all the rest, titanium and calcium, phosphorus, without all of those materials, it's very likely that no planets can form around stars in a globular cluster because they were never made with any such elements, and they were never around any such elements.
And they're separate. They're plunging through our disk because we know that they're newer because there's less elements. If they were part of our galaxy, they would be included with more elements. Is that how it is?
Not exactly. Okay, they're among the oldest stars because the newer stars are formed from elements that are now in existence. Okay, we were formed in a solar nebula. Right. In this solar nebula, we had iron and silicon and all this material. Well, the star that forms the heart of our solar system was formed with those elements as well. Mm-hmm. None of it's in the core. The core is the hydrogen, the compressed hydrogen, right? And if there's any other elements in there, they're not hot. It's not hot enough to fuse them. Okay, the envelope is full of all this other collection of materials that was made with the star. Right. Along for the ride. Okay.
So gravity pulled in.
That's right. Gravity pulled in. And now that's right. And the remaining amount made other clouds around the star as it formed. And they, of course, orbited the star formed an accretion disk, this disk of material. Right. And it started clumping. As it clumped, it made Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. It's a planet. I'm sorry. I don't disagree with any of that. Okay. And the asteroid belt was a belt of what could have been another small planet. Okay. But the presence of Jupiter out there prevented these particles from actually coalescing into a planet. Okay. Because as the asteroid belt went by Jupiter farther out, those asteroids be tugged toward Jupiter and then go back to their normal orbit. And that slight tugging every time they go around was more than enough over millions and billions of years to prevent a formation of a planet. Now, it wouldn't even be a planet. If you add up all the asteroids' mass, this is a little.
Oh, yeah.
Yeah. You add up an asteroid's mass, or all the asteroids' mass that we know of in the asteroid belt, it adds up literally to about a fourth the size of the moon.
It's crazy. It seems like it's huge.
I know. But that's the perspective that you get when you see representations of the asteroid belt. You see this gigantic mountains of, wow, that must amount to a giant planet.
Yeah.
No.
And that's small. Different than the Oort cloud, correct?
Yes. Yes, we have the asteroid belt, which is actual established belt. Then
in the middle,
that's after Mars and before Jupiter, and then we have farther out past Neptune and Pluto, a planet. Okay, we have the Kuiper belt. That's spelled Kuiper, and that's the realm of the icy bodies. And we noticed there are some larger objects out there similar to Pluto. Sedna is one. Okay. Makemake is another one. There's a bunch of them out there. And then beyond that, we have an Oort belt, which is a belt of further icy bodies further out. And then farther out and encompassing the whole solar system is the cloud you're talking about, the Oort cloud.
Right.
Now, how big is that? The Oort cloud stretches literally more than halfway to Alpha Centauri. So it's going out a couple light years.
Is it a sphere or is it a disk?
It's a sphere in the Oort cloud, but there is an Oort disk too. But there's all our planets in their orbits. Then we have the asteroid belt after Mars, and then Jupiter, Saturn, Uranus, Neptune, Pluto, and then beyond that we have the Kuiper belt of icy bodies. That's a relative belt, and beyond that we have an Oort belt. Oort spelled O-O-R-T. I know.
Oh, okay.
It's someone's name. Okay. And then we have that cloud, the Oort cloud. Okay. And it's it's been romantically characterized as the realm of the comets. But in fact,
how romantic.
It is, but it's so far out. And in fact, stars moving through the universe and around the galaxy perturb these things, and some of them end up getting slowed down, in which case the gravity of the sun can pull them in. Yeah. And they make an orbit, and maybe they leave after that. Or maybe they become periodic comets, which come back in these highly eccentric or highly elliptical
just like
orbits.
We need to do
in a few minutes.
Leave and come. No, right now.
I thought we had to 57. Okay, I'm sorry.
It's 54. Well,
folks, thank you so much, Tara. Thank you.
Yeah, well, thank you, Mark. It's
Great
fun.
questions,
So
Nicole.
interesting.
Yeah. Well, folks, see you later. Thank you for coming, and we'll see you next week.
Thanks, everyone.
Bye-bye.
Bye.